Hello, can you hear me? Yo. Hello. Sorry, I forgot to turn on my mic. So this is the color correction, and then this is not. But I think because of the background, it's too bright. But if I cover up the camera like that or something, but yeah, then it's bright. But if you say to remove, then fine. It doesn't look bad, right? It's just because of the closer shade. Let's try then. Yeah. It's this side, right? No, this side. Better? Oh, it's just my camera is shit. Let me see. So if I vertical cam, let's see. It's still dark, isn't it? Webcam. How about I do some things? Now it's way worse. Wrong side. I think this is better, right? Oh, it's supposed to be the behind one. God damn it. Let me try on this. Whoa. Okay. There we go. Better. Much better, I think. Yeah, it's much better, I think. And if I configure some things, oh god damn it, this is fucking cool. Not this one, this one. Yep, it dims. Why does it dims? High. Okay, it's good. All right, not bad. Okay, that's much. That's what I can do. Okay. So how you been? Is everything going good? We have matplot, so recipe, matplot numpy. Oh, it's trying to divide. Okay. Not much. What is this font? If I don't have this, what happens? Oh, you don't have a pie chart. Oh, this is the pie. I don't want the legend, right? And the bowl, what's the bowl? The size. Get it? Okay. And then the title, no. I see. So so this is what pick data split recipe. Okay, recipe split 0. Okay, and then you pass in data. Where did we get this thing? I see. Wait, no. Lambda. How about I remove this? What happens? So if I run this, get G. I guess I don't want this part. Then I get that one. So that's what I need for here, right? So yeah, pretty much. So the data is not there. And what is ingredient? Do I need? I don't need ingredient. Okay. Makes sense. Okay. So first I need to create my data. The one I need to label, right? Which is here. So what if I do print India? I get 40. Okay, that's good. So I'll put in numpy array and normal array. Okay, so array minus, and then I have. Oh, this is the whole. Data science. Yeah, I'm taking data science this semester, so this is the data science course, and yeah, it's an assignment, but I'm trying to figure out like how to add the labels. So what I mean is I want to add like 1760 in the United States, like below here, like this, and then yeah, ChatGPT, nah, ChatGPT are for losers. Just gonna Google myself. Actually, ChatGPT is learning from us, right? So we are. I bet ChatGPT can answer this, but you know, I want to practice Googling skills too. But the thing is now that I have like bunch of 10. Yeah, exactly. I don't like training ChatGPT too, since it's because I mean, I don't know, like what I heard is like the OpenAI is doing like some, how do I say, I don't know how to phrase this, but I heard I saw an interview that like some rumors about ChatGPT, you know, they're using the data and stuff, blah blah blah, and then the guy recommend like, you know, the best thing is to stop this, is to stop using or stop feeding into ChatGPT. And at that point, well, I think it was like 3 weeks ago, and at that point, like, oh wow, it makes sense. So it's like, yeah, I won't use ChatGPT anymore, you know. But before I before the interview, before I saw the interview, I was using it. But after I saw the interview, then I stopped using. But it was something along that line that it was saying like ChatGPT, you know, use the data, blah blah blah. You know. Yeah. I mean, basically I'm running on some media opinion about some guy, I don't know, but for me it makes sense, so you know. Yeah, back to track. So what I was doing, yeah, I was trying to add a label. So we have 10 countries. It's impossible to extract each and individual one countries. That's not good. But how could I one thing I can do, I can loop through this guy and then get all of this to an array. But then is it this how you do? You put in an array and then you put a label? Is there a better way? I guess that is the way. So for I in, how do I loop? So I want to loop through the countries. So count countries, right? And then if I print I get country. So I have to do iter rows, right? And then this would be lab and then rows, and then once I do like rows, get this. So if I do row and then title, I get all the data. Perfect. And then I want to append this data to the my list. Okay. And then my list would be this guy. Oops, that's wrong. It should be append, and then so once I have the data in my list, what I could do is I could use the technique here, which is write this function. This, do I need this? Yeah, I need this because of something. It does something. So let me try to copy this first in here, and then we will do data and yep, this guy. Okay, so it would be all. I see. So this would be here, and then /n, and then you would use the lambda things to put in here. And if you run, ta-da! Oh, god damn it! Something went wrong there. Wait, that's not right, is it? No. What? Oh, not this G. 100. Wait, no. What the fuck? It's supposed to be like this, I see. So if I do like that, then I get the percentage not with the G. So the percentage is correct, right? India is 12.4, okay, but the data but the United States must be 1776. So if I print the list, okay, 1700, okay, I see, it's supposed to be my list. There we go. Ta-da! We got it. We got it, boys. We got it. We got it. Yeah. This is wrong. 6. Australia must be 47. Okay. Why is this wrong? Absolute? What the hell? Yeah. So I need to understand this a bit. Okay. So, oops. They're playing Code Wars. Ew. Okay, but what is this? Oh, it calculates the percentage. Absolute? What do you mean? Okay, but why I have to do this? D. Is it a thing? No. So if we do like what? Ah, I see. So if we do the format string, and then if I do like that, and then if I do absolute, I get that, but if I do D, get the same thing, right? So so India should be 1/6, so United Kingdom is 160. Wait, that's off a bit. What time is it, Super? Supervisor? 160? 159? What? Why is it 160? Wow. 1 a.m. Really? Austin is this. Oh, you're in same time as Austin. Is it 1? Where do you live? 1 a.m. New York, right? 2 a.m. Sydney. So wait. Okay. So this is correct, right? Texas? You live in Texas now? Wow. What? This is 156 and 50. What is this? Japan is 140. What? Why does it get like... Wait, I get the data. No. I already have the things. So if I put this, whoa, not the list, dumbass. How about number 1? No. if I use this guy here, then never mind. Whoa, what the hell? Okay, so why does it I guess I have to tell my teacher then. My donut, and this is his donut. Oh, I need to make the X label too. Plot title, and then we need the number of titles released by top 10 countries. Yep, so to replace, boom, and then this one is his. Shoop. And then go to Microsoft Teams. Where is he? Okay. So the country like so United Kingdom is off. Okay, United Kingdom. Let's see. Okay, United Kingdom is off. India is correct. Canada is off too. So Canada. And then what else? Canada is off. Spain is correct. South Korea is off. Let me type it here. South Korea. Japan is off. Japan is off. France is off. Mexico, Australia, and Japan. Yep. Off. Do we have to put comma here if I want to? So comma is independent clause, right? Am I correct? Is it supervisor? So it's like you set thing and right? Is that it? It's I don't know when to put comma before and when to use. Okay, so so example, the dog is young, well trained, and okay. Okay, so when should, okay. Independent clause here, right? Yep, so in this. Whoa, my battery is low. Should probably charge. So, supervisor, you moved to Texas to like move to Texas because you got a job, or you moved because some reasons that now I should put this guy here. So donut, you fucking donut. Okay, and then we do that. Okay, so this doesn't matter anymore. So I need to understand what is this first, right? Mouse. Dun 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 dun. Donut. Donut, I'm gonna be like a donut. Okay, so you have a list, you put in the list, you increase the size. I guess it's too big, so let's make it 15. It's too big. 6, 5 and 5. It's too small. 8 and 8. Too small. 10. 15. Nope. 10. Nope. 12 and 12. Yay! 12 is correct. Yep. So okay, this is my list, and then you have a function which taking the value. Absolutes means that you do numpy that round. So I don't quite understand what is. So what is this thing? These are my data. How? I see. So this is like a built-in thing that you give, right? So you do the lambda, and then you pass in this. Oh, good shit, and you pass, and then you get the thing, and you round. So you round. But why? Why do you wanna round this? Just make it int, you fucking stupid. Let's make it int. Then it's correct. Oh, I see. Wait. So you have the data. Hey yo, Joel. Is it? I pronounce your name correct? I don't know if it's correct. Yeah, yo, what's up? So, this is, so it's rounding. Absolute. Joel, yeah, I got your name. Pronounce your name correctly, yay. What the hell is this? Okay, get the data. Why? I need to separate these things. I like math and I never coded. I like math, but I haven't coded, and I'm 15. You think computer science could be fun? So you like math, but you never coded, and you're 15. I think you should try, you know. You should try, and to be honest, and I'll be completely honest with you, computer science is not programming, right? There's two different things. Okay? If you want to do programming, do programming. If you want to be computer scientist, do computer science. And what I mean by computer science is you come up with things, you come up with theory, you learn how computer works, you learn math, a bit of math. Okay, let's put it this way. If you learn computer science, it doesn't mean that you'll be developing like web app, mobile application, or etc. Okay, I hope you get that point. That's what I mean. But you would rather learn like theory, how it works, what is the math behind of it, and you will learn like computer network, what is TCP, what is IP, what is WAN, LAN, what is all this crap, right? But you won't know how to do it. You know what is thing, but you don't know how to do it. But if you want to build, if you want to make games, you want to make websites, you want to make you want to do data science or something, you want to make mobile application, then do programming. You know, easy way, click on this tab, hit go YouTube, boom. What do you want to learn? Mobile development, yeah, tutorial. Why did I? Boom, here, do this. You know, this is a university, and then you do a bunch of projects, then you'll be good at it. You know, that's what I mean. Computer science doesn't make you good at actual programming, good at making software. Yes. Yep, exactly. You understand how it works, but you don't necessarily know how to do it exactly. But nowadays there are courses like web development and like data science, like this. That's what I'm doing. There's courses. It's improving, but it's not better than what's on YouTube. The on YouTube is far more better than what you professional. That's what, you know. But depends. if you want to do things, but the saying, there's if you see a university with saying, oh, we have mobile development, iOS, Swift, Android, web development, learn JavaScript in university after you finish computer network, calculus, blah blah blah, and you have foundation, you reach the courses that web development is as, all right, is some university might be better, but it's not better than YouTube at all. That's it. But the calculus and stuff might be, might be better in YouTube, but depends. Yeah, it's good that to be useful sometimes to help someone, to guide someone, but take my advice as a, don't take it as what I mean, but try to interpret and like try to see what is right for you. I'm just saying in my perspective, doesn't apply to you, but some university might be very good, they have very good facility. Then if that is the case, join, but try to do research, find along. Yep, exactly. But do your research and see what are the courses, try out. Yeah, but it is what it is, and it is what it isn't. So I have to what's new data science. Yay. University, this one, data science, and week 2, the week data twin, and we will do home review. And home review will have testing donut fun. Paste there. What the actual fuck is going on? Paste. Nice. So it is data science. I see it's a pie chart and stuff. Yeah, it is data science. This is the university course that I'm doing, and they teach bunch of these things, but most of the things I learned from YouTube, not from the university, but it's a good guide what to do. So I have a worksheet that my university gave me, so I'm completing. So I'm in the last task. Once I complete, I will go to, I guess, computer network, no, math and stat, and then I'll start reviewing. I'll open some iPad. You guys will see some iPad stuff. Really interesting stream today. Yeah. So what are your interests, Joel? Are you just figuring out things? You said you like math, or so you're in Thailand? Yeah, I'm in Thailand. How do you know that? Did you hack my thing? Man, 15 years old, no shit now, huh? I'm honestly just figuring out. Okay, it's good. It's good. Try to, figure out what you like, what you don't like, and then Thai. I see. Yeah, I'm Thai. I'm from Thailand. Yeah, proud to be Thai. So what was I doing? Okay, I was doing something this. Alright, so this is my data set. Give me my data. So this is my data. Copy this, put it up there. My lovely list. Boom, and then you have to import numpy as numpy. And then, wait, do I have numpy? Anaconda, activate Data science, please go. Very good. Whoa. Okay, that's good. I love anaconda. What just happened? Okay. Okay, so I have the data. Oh, I shouldn't test here. Fuck. Stupid. I should copy this. Then go down. Wait, what the? No. Okay. I should get this thing, copy, and then go down. Press here. Okay. So now I have. So did I get a donut? Okay, I get a donut. Yeah. So I have my list. I get the okay. I have a list. That's my list is good. Okay. So I'm trying to figure out how this function works. So it rounds this thing and times the what the hell? Okay, it rounds. Wait. So print. So divided by 100. It's what? Okay. What? This. Okay. So you divide by 100, and then what? And then you multiply with the sum of the all values. What? Why you do that? Okay, so let's see. So if I do print numpy sum all values would give me these things. Okay, it's about correct. And then if I take this, I multiply this guy 11611. But what? But I don't need that, right? You round. Okay. That doesn't make sense at all. I don't need this, to be honest, you know. I have my data, right? I don't need to do all the shenanigans. I have my data, that's good. Okay, and then what? My data is what? No, that's not right. Okay, so if I do like that, then what it says. Okay, this is confusing. Oh, I get it in a list, like a printed one. No, I don't want to do this. No, how about I just put it like that? Do I get the same thing? No. Round. No, not round. What's this? So round. Okay. Whoa. This is interesting now. Why does this give me individual value? What the hell? What is this type? Class in. What if I do? Wait, it's the same thing? What is in this? Class list. But if I put int, it's I don't understand why. Okay, this is interesting. Whoa. No, crap. What? Is this tab? No. I don't want tab. This won't work. What the hell? Come on. I want tab. I don't want tab. I don't want tab. Yeah, use hate it. Hate it. Show me love. Boom, boom. Boom, shakalaka laka la da da. Configure, add a new interpreter, add a local, yep. It is in, not this one, but Anaconda environment. Load the environment, not this one, but data science, yay! Okay, so use this. Whoa, CPU's nuts. It's heating up real bad. Would you use scientific mode? Yes, please. No. Okay. It is initializing. We have to wait, otherwise Okay. Okay. Whoa. Here. Okay. Ew. No, I don't want the scientific review. Give me the normal appearance. Scientific note, no. Give me the normal mode. Oh. Can you just give me a window to show and not here? Because I want to see the code. Run. Not there, you stupid. Run. No. I don't want scientific mode. Reset font size. No. Okay, I guess I have to just run it. Run it from here then. What is it? Home review running. Yeah. So this is my chart. Okay. So how does this work? Okay. Make it file. This one. So you have that one, and then you do this. No. Get that. Oh, I see. So you want to get the individual one every time. So we can That's clever. Yeah, that's good. And I get the point now. Boom. Bye. Okay. That's good. Ew. But my red quit is not working. God damn it. Start red quit. I mean, trying to maybe red quit. Why it's not working? Red quit. Red quit. Yeah, activate. Yeah. Yay, activate. LS cancel. It's not quitting. Oh no, oh no. Why its red quit is not working? Whoa, cocksucker. Thank you for the raid. Sheesh. Hi, my cocksucker. I'm a pussy licker. John, it's me, your new setup, Dad. What? Name one pussy have you licked? One? Yeah, so I was doing some data science, a school worksheet. Apparently, the numbers are quite off. So I'm asking my professor, and professor is not answering. Ouch. Hurts. School. Don't be negative about school. Come on. And other things is I was trying to install Red Quit, and then the terminal is open. I try to hit this terminate, but then the terminal is still running. Essentially, I want to be like boom when I hit the red button, but it's not working somehow. And now I demonstrate you, and my notebook fucked up. Nice. Oh, whoa. Okay. It's 80. So okay. Man, you guys asking so many questions. Wait. Then my number is 02. Donut. I should eat dinner. Okay. John Striker said you should mod me. I should mod you. Do you stream? Do you even stream? Imagine learning to code in university in 23. Nice ride. Ride a bike and knock on the professor's head and answer talk. And yeah. So anyone know how to make this application work? Red Quit. Apparently it's not working. It's not quitting. So let's try on. Let's open some application. Let's open this. Okay. Cancel. It's not working. supposed to quit like this. Oh, is it because of the settings? I don't think terminal app support closing app when. I think terminal app support closing app. No, this shit. This is shit. So, like, okay, I want to demonstrate you. I click this, right? Okay, I expect this to not come up here. You know, this is so annoying to come up here. That's what I want to quit. When it's quit, then it's not here. That's the point. I don't know, this anaconda shit just open here, you know, and doesn't mean that just this application, whatever, like if I open like Postman, right, and then okay, I say, oh, I don't want to use anymore, boom, okay, I want to do this. So once I want to switch, I don't want to see Postman here anymore. It's how Mac work. Yeah, press Command Q. Yeah, but it'll be easy if I like just like Postman and then I don't want to use Postman, you cocksucker fucking shit. Boom, done. Okay, go. You know. I have to close. Too much crap here. You know, it's just too annoying. Oh wait, but then the red quit. Oh wait, I think this would work, right? Now, boom, boom. What? Really? Option click? Option click? No, you fucking liar. Here, option. Wait. Okay, this is option. No, it doesn't quit. Okay, so what do you oh, you okay? Yeah, that was cool. If there was thing, yeah, like that, yeah. Open Postman, press tab, keep on holding, and move mouse to Postman, and then press Q. Whoa. Okay, that's good. Okay, fine. Guess too many Mac lovers here. You just wanted me to use the Mac way, huh? Too many Mac lovers. Alright, fine. Okay, let's do programming. Fuck Windows. Fuck that crap. Terminal sucks. Okay, Vim doesn't work right. There's no apt, there's no brew. Fuck, how can I program that shit? I open terminal, have to use some crappy shit, and my, you know, when I go here, I expect to, if I cd, everything should be here. No, Windows should go here, and user, and then my name, and then once it's, no, it's not this, user, and then public, my name, and then some shit. Fuck Windows, hell no. I'm gonna stick with Unix. No, fuck this. Just use Linux, that's it. That's brew. No, it's fake brew, it's ladyboy brew. That fucking brew sucks. You know? Sucks balls. Windows sucks balls. You have to go with shit, and you cannot, okay, once I like here I can see everything. If I want to see hidden files, I can see, and Windows have bunch of hidden folders. fuck dot some shit. Fuck that. Never use Windows. Never. I mean, never. You can use Windows, but never use Windows Terminal. It's crap. It's bullshit. Okay, so we have our data is off, and okay, so it's here. So we have 50. This is correct. India is 12.4 and 434. That's correct. United Kingdom is 10.3, 359, but I got 360. Why? Porn is better on Windows? Really? Because of the GPU, very good GPU, so it renders, you can see the pubic hair, you know, even the pubic hair is blonde, you can even see it, you know, even it's a white girl with a blonde pubic hair, you can even see it. That's what GPU is for. But I don't know why this data is off. But this is correct, right? So previously we have like Australia, blah blah blah, and then United States. Okay, and then this is right, but how did the data got messed up? What? Didn't professor answer? Well, yeah, he's what? Away? Free all day. It doesn't answer really. Okay, never mind. I guess I'm done. I'm done with this programming. Now we will move to what we call is bye bye. Bye bye, and then what do I have? Word document. Go. Discord. Okay, so today we will review maths and statistics. So I know there's some people who are very good at maths in this stream, so I'm gonna ask you. There's MC. By the way, if you don't know MC, it's a fucking some rocket scientist, physician, some physicians, some physics something, right? And then he transitioned to programming, so I guess he know a lot of math, so I expect you to help me. Oh, stop it. Okay, so what did my Apple Pencil die? Hello? Okay. So so I will pull up my iPad so you guys can see. This is up there. Here. Then this is supposed to go here. Ship. Boom. You wanna connect? Yes, sir. I trust this computer. Okay, and quick time player, and then new screen, new movie. Whoa, not this one. And then no, what? New screen record. No, new movie. Oh no, new movie. And then where's my iPad? What? iPad. There's no iPad. Okay. Quick time. This one. Movie. And then iPad. iPad. There's no iPad. Okay. iPad, yeah, iPad, yes, iPad, Yay! There we go. We got an iPad. Hooray! Make this bigger. Okay. So, where is it? Where is it? Math and Stats Week 2. Oh, have you guys ever read this paper? This is really good. Rapid object detection using a boosted cascade of simple feature. Have you ever heard about that? If you haven't heard about that, what the hell? Okay. Yeah, this is a paper where some computer scientists named Paul Avila here came up with an algorithm which detect faces with cascade. So what it does is it sees that our eyes are darker than our forehead, and our forehead is brighter, and and it's pretty interesting. I haven't read this paper yet, but it can detect like this. Yeah, have you ever seen like the old camera where you hold it like this and then you record? What's that called? You like have a grip here and a small, and then you have a screen like this and you record, and there's a a mini box that detect faces. Yeah, this is the guy who created that algorithm, and they implemented in the camera. So what is it, like audio detection? Yeah, like this. Have you ever seen in a camera? Yeah, I saw in this guy explained it pretty good.
Well, I'd like to talk about face detection.
I'd like to talk about face detection. You see this guy? See this? This is the algorithm. Cool. So we were doing probability, basic probability. We know this is Bayes' theorem. Okay, Bayes' theorem. So we have week 3. So we gonna learn about descriptive statistics. Good, let's implement on the stream. It's too hard for me. Okay, so we are in descriptive statistics. Okay, so so we have sample mean, we have sample variance, and we have sample standard distribution. Oh, deviation, not distribution. Deviation. And then yeah, so point estimate. Okay, so I have to learn this. Sample mean. So what is sample mean? So you have ChatGPT. This is what happens, when a dump. Whoa, not this. Is it? Ah, I see. Whoa, not good notes. Yeah, this is what happens when when you don't know a lot of things and you have to learn a lot. So this is called X bar, from what I remember. X bar and X bar, right? So we have this is to represent sample mean. So it says that the summation of xi and so what this mean is, and correct me if I'm wrong, okay? So what if we have 1 2 3 4 5 6 7, right? And then we take, this is the population, right? Population, and then we want the sample, so we take some data from the population. So let's say I take these 4, so 1 2 3 4, so 2 plus this is 5 plus 4 is 9 plus 1 is 10, right? Did I do the math correct? 4 5 6 7 8 9 10. Okay, so our sample is 10, right? And then 1 2 3 4, if we divide it by 4, we get what? 2 2s are 4, 2 5, 2.5, and we need a scientific calculator now. Okay, so 5, so this is like 2.5, right? So sample mean is to calculate that one, right? Or either way we can do like the formula way is you take 1 n, so n is 4, and then you multiply the summation of 2 like this, and then summation would be 1 plus 2 plus 3 plus 4, right? And then it's like this. The calculator Python. And then you do 1 plus 2 plus 3 plus 4, you get 2. Yeah, and this would be 5 by 2, which is 2.5. This is the formula. Okay, so we understand what is x bar and sample variance. So I'm not quite sure what is sample variance, but I have an audio where I record my professor. What is this? Whoa. Can you hear this? After I connect your oh, this is ecology. Ecology week 3. Okay, so math and stat, right?
Yeah, we're just going to dig deeper today into what they teach on them actually. So there are 2 parts to this today's lesson, as usual. Okay, but this time the second part, okay, computing percentiles, plus.
What? Working on quantum compression in JavaScript? Serious? Fucked up my computer. Okay. Sample variance.
Histograms, Okay, we've actually done using Excel or sheets, Google Sheets. So if you have your tablet, if you have your PC, that's good. On your Mac, that's good. If you have your phone only, you might have a problem. Okay, but you still can do it on phone if you want.
What? Someone called me. Hello, Steve Jobs. Yeah, that was Steve Jobs just called me to go attend a meeting. Yeah, attend the meeting. So I said like, "Fuck you," and then he said, "Oh, it's okay." And yeah, that's what happens. So sample varies. Sample variance. Okay. Wikipedia takes 1 second to read. Okay, let's see. Sample variance. Given a number of observations, their sample variance measure how far they are spread apart. It is also a estimator of variance of the population in which observers can be drawn. Given an n observation x1 to xn have a sample mean. Okay. There are two main ways to compute sample variance. Unadjusted sample variance, also called bias sample based. Bias or base? What's this? Bias? Base?
Biased.
Yeah, bias. Yeah. Adjusted, unbiased. Okay, so our is what? Our is this one. So it, no, our is this one. Is it the same? It's none of the same. Example, suppose we observe 4 realization. So okay, their mean is this one. Okay, divide the sum of the squared deviation from the mean. Divide the sum. Oh, okay, you square the difference. Oh, I see. So you take the mean is 5 and then you divide the sum of the square. So you minus the mean, the x bar, the sample mean, right? And then you square it. Once you square it, you get this one. By dividing it by the number of options -1, we instead obtain unbiased estimate. To calculate this. But why do we even need this sample variance? You know, Why do we even need that? Sample variance is used to calculate the variability. What the hell? Variability. So like the lack of consistent or fixed pattern. Variability of change. Okay. In a given sample, a sample is a set of observations that can be pulled from population, okay, and can completely represent it. Okay, the sample variance is measured with respect to the mean of the data set. It also known as estimate variance. As data can be two types, a group and ungroup. Hence, there are two formulas that are available to calculate the sample variance. Therefore, the square root of sample variance result in sample standard deviation. In this article, so sample this one, right? Nice move, sir. Thank you. We elaborate. Sample variance. Sample variance is used to measure the spread of a data point in a given data set around the mean. Sample variance is used to measure the spread of the data point. Okay. All observation of a group are known as the population. Okay. I don't understand that bit. When the number of observations start increasing, it becomes difficult to calculate the variance of the population. In such situations, certain number of observations are picked out and can be used to describe entire population. The specific set of observation, a sample, and the variance is also here. Can be defined. Sample variance can be defined as the expectation of a square difference of data. What? Can be defined as the expectation of a square difference of a data point from the mean of the data. Okay, suppose that they are given as 3, 2, 21, and 9. The mean is this, okay? Of the data set is determined. The mean is subtracted from each to get this number is divided by 1. But what does this says? It says nothing. Suppose the data is given as the mean is this. Is it really the mean? Is that one? 3 plus 21 plus this one plus 9. 1, 2, 3, 4, 5. 29.6. Okay, the mean is subtracted from each data point and the summation of the square resulting. This given wait, really? I don't. Anyone know? Can anyone explain? Because I don't get it. So we have So it says that we have 321, 7 and 9, right? And then the mean is 29.6. And then if you want to find this thing, do -1, so it will be like 1 2 3 4 5. So okay, so if I type that in a calculator, we get 3 minus 29.6 squared plus 21.29.6 squared plus 28 minus 29.6 squared plus 17 minus 29.6 squared plus 9 minus 29.6 squared. You get I got, yeah, so we get 1. Okay, but does anyone know why this number matter? Like this is, but it says like how spread okay. But what? How is this? How is this? How does this represent it? You know? How? YC? Cam is not clear. Cam is not. Cam is not clear. Oh, camera is not good. It sucks. So this is the thing. see.
Okay, so let's begin. So we call descriptive statistics as points, okay, estimators, okay? We specifically call them point estimator, namely because they actually require to create an estimation, right? An estimation that is just only 1 point, okay? That's just only 1 point. Take, for example, when you actually take averages, right? Averages. So I take the average of all your courses, basically, and turn them into GPA, right? GPA, grade point average. So if you have a GPA of, say, 3.2, what does that tell you? What does that say about this particular student? If you have a GPA of around 3.2, what does it say about the student? Pretty good, right? Okay, above 3, pretty decent. Okay, if you have a GPA of 3.8 to 3.9, really, you know, high performing students, correct? Okay? Sounds pretty simple. Now, what about if I have a GPA of 2.8? What does it mean? 2.75 then. Does that make a difference in the way that we look at things? How? Bad performance. 2.75 is bad performance. Not that bad performance. Average students. Okay, sort of an average student. Why do we say that this person is an average student? Is it because we're expecting the average to be around 2 point something? We're expecting that, right? You just mentioned it, like I said, average, and if you have a GPA of 2.7, then, and you said that this is an average student, so it means that somehow you have, you know, this idea that, you know, the spread of students' GPA across the university is around that. Furthermore, is it the same in ABAC as it is in Chiang Mai University or in Yale or in, you know, where else? Chulalongkorn and all that places, right? So these point average, okay, only say that much about, you know, the average and so on. So a student having 3.99, what does that tell you? For starter, if the person has taken already, like let's say, 40 courses or 50 courses and they still got 3.99, what are likely their grades? Like from each course. A, they probably missed out on one, which is probably like an A minus, and the rest is just A, right? So you can pretty much, you know, say that if a person gets 3.99 GPA, they probably got like lots of A's, mostly A, only one A minus. But what about if the person gets 2.75? What does it mean? Does it mean that that student gets 2.75, or what is 2.75? B minus. Does that person get B minus for every courses? Could be an A, could be a C, right? And a combination of all these that makes up 2.75. So it means that that student may excel in a certain area and perform poorly in some other areas. You don't know that, right? So the GPA only provides you with a point estimate, okay? And the simplest statistics that we normally use is point estimate because they are easy to compute, they are easy to interpret, but they do not actually represent a lot of things. You cannot make deductions about that 1.75. So it means that that student may excel in a certain area and perform poorly in some. Statistics that we normally use is point estimate because they are easy to compute, they are easy to integrate, but they do not actually represent a lot of things. You cannot make deductions about that particular student. If they get only 2.75, maybe they get A's in programming and database systems and math courses, but maybe a C in, I don't know, what else do you study? Word heritage or something like that? What is it called? Yeah. What is it called? Exactly that? Oh, wow, pretty good. Word heritage and ethics and stuff like that. Right, so maybe they are pretty good with, language courses, pretty good with logic courses, maybe not so much on language courses and theoretical courses, or those ones that require a lot of memorization, right, and so on and so on. So point estimates, okay, that's what it means, and this normally comes with this word, variability. This is one thing that most standard normal human beings don't actually go for variability. They only want to look at points, right? So just like in the example that I gave just now. .75 only tells you the points. It only tells you that on average this person is a B- student. But it does not mean that we know anything about the variations in how he or she performs, right?
Variation. Variation. Perform. Is it like perform?
In the range of courses, okay? So we also need to know how to compute the variations, okay? The variations, and then we also need to know how to express all these points and variations, okay? Visually, as well as, of course, descriptively, okay? Descriptively and visually. So that's why we're going to be talking about percentile, box plot, and histogram as well. Okay? So let's start easy with summary statistics. Okay? With summary statistics. So the first one here is this guy right here. The standard mean. You guys already know this one. It's actually the easiest to compute, right? You got the data, you add them all up, you divide it by the total number of
over how to calculate the variance for a sample. As you see here, the notation is S squared, which represents standard deviation squared, or the variance. Just getting into the formula, we have the summation of each x minus the mean squared over n minus 1. And the sample I'm using only has 4 numbers. It's 2, 5, 9, and 12. The reason why I'm choosing such a small sample is because it's about the process that matters when you're calculating it by hand, and that's what I'm showing here. This is to help you understand how the process goes so that when you have a test, when you are asked about it, you know how to do it, whether it's 3, 5, 10 numbers. The first thing you have to do is calculate x bar, or the mean. So it's the summation of each x over n, which equals 2 plus 5 plus 9 plus 12 over 4, which gives you 28 over 4, which gives you 7. So a nice number. The next thing is to calculate each x and subtract it from 7, or the mean. Square it and then sum them all up. So we have 2 minus 7 squared plus 5 minus 7 squared plus 9 minus 7 squared plus 12 minus 7 squared, which gives you negative 5 squared plus negative 2 squared plus 2 squared plus 5 squared, which gives you 25 plus 4 plus 4 plus 25. Remember, when it comes to negatives, when you multiply a negative with another negative, you get a positive. Finally, we get 58 when you add them all up. The last thing here is to just put it all back into the formula. So we have s squared equals 58 over n minus 1, which equals 58 over 4 minus 1, which equals 58 over 3, which equals 19.333. If you wanted the standard deviation, all you'd have to do is take the square root of 19.33 repeating, and you'd have your standard deviation for the sample using these numbers. So this process is obviously very similar to finding the standard deviation. It's just a matter of where the square root is. So that's why I'm using the same numbers over and over and over again, because again, it's the same process. It's at the end that matters, and it's to help you solidify it in your head if you're watching each video. I understand from teaching the class, especially those that it may not be majoring in a science or math, that it's helpful to use the same numbers and then show them where the change is so it gets solidified in their head. If you found this to be helpful, please like for videos.
You'll come across a few different formulas in statistics for the sample variance, but this formula here is the most common formula. It's the sum of your x values minus the sample mean, that's x bar, all of those squared over n minus 1, and n is your sample size. Like pretty much everything in statistics, there's a couple of ways to tackle this. I'm going to use a table to show you how to find the sample variance. In the first column, I'm going to put my x values. Those are my x of I. That just means all of my x values. Let's say I have a data set, and here are my numbers. 10, 15, 21, 32, 45, 59, and 63. I want to find the variance for this sample. In my next column over, I need to find the mean. That's x bar, my sample mean. Well, to find the mean, you add all of the numbers up, 245. I want to divide that by the number of items in a data set. There are 7 items, so 245 divided by 7 gives me my mean, my average, and that figure is 35. So the mean for my entire data set is 35. Next column over, I'm going to work this top part of the formula here. X of I minus X bar. So I'm going to take my X value and subtract the mean. 10 minus 35 is negative 25. And I'm going to work my way down the column, just subtracting the mean from my X value. So I've worked out my X value minus the mean. The next part of the formula tells me I have to square those values. It's this entire part of the formula there.
The man tongue. What's up, Mad Flash? It's been a while. Where you have been? It's been a while, right? What are you doing? I'm studying maths and stats. Also, I'm doing the data science. ML? Not ML, but data science. Yeah. It's my university course that I'm taking, so it's ML. Data science, not ML. This is wrong, I guess. The course is about learning data science and yeah, of course it's just about data science. Like, so how would I say? Let's see. Analytics, yeah, something like that. So first, in the first week, you learn about like basic and then data processing. Data processing is how you get the data from the internet, like could be web scraping, it could be any sorts of data. And then visualizing, so it's like data analytics. So it visualize plot graph, bar chart, box graph, line graph, pie, donut, and then we will have exploratory data analysis, which is you make a machine learning algorithm to explore the data to find insights. Once it's done, and then you will learn like machine learning statistics and stuff. Basically, it's just data science, like, you know, how to get the data, how to clean the data, how to visualize it, and how to predict and make a model to predict. Yeah, seems hard, but it's not that hard. Okay. So I think I should submit this one to my data science. This one, right? Yeah. So what have you been doing, Matt Flash?
So all I do is square these values. Minus 25 times minus 25 is 625. That's 400. 14 times 14, 196. 3 times 3 is 9. We've got 184. This symbol here, which just column here. And if I add all of these numbers up, I get 2,690. So I've worked my top part of the formula and I've got 2,690. The bottom part of the formula tells me I need to divide by n minus 1. Well, n is the number of items in my data set. It goes on and on and on.
Dude, if I would you back in uni, I would use it. I get your point, you to use ChatGPT, but what just happened? The thing is, I don't wanna train the ChatGPT. I don't wanna feed the data in, because I heard an interview like from someone that ChatGPT is using in the wrong way, and like for me that guy makes sense. So from after watching that interview, I stopped using ChatGPT. Before that, I was using, but after that, it isn't the right thing, but I guess it will be much faster for sure, but nah. So you're the real one. Thanks, man. You too, man. Freedom. Does anyone know degree of freedom? Degree of freedom. Oh. Is it? Nah, it's still the same. Still, let me copy down. You heard about it too? Wait, let me. I'll read your message. Let me. Real material. Thank you. From what I understand, university material is everywhere and worthless for them. But by the way, there are options to not share data as well. I heard about it. Really? There's not an option to share? Then yeah, I will kindly use. You see, before I used to use a lot, but since it was some things that, you know, settings, share links, export, manage. Nah. Screw it. You're using I mean, you're right, I'm using Google, but I'm not saying that they are okay. I know Google track me and stuff, blah blah, right? But at least if I'm not using ChatGPT, I'm not feeding the ChatGPT with the data. You understand? So if I ask something, I'm not feeding in my input, my data inside. So that's what I mean. I'm not feeding in. You know? It's 20%. Okay. Yeah. It's just my opinion, you know, just my opinion. But I agree on your point that ChatGPT will make my life much easier, and you know, it'll be quicker and easy to understand and much better as well, I think. Well, I'm not sure if it's much better, but it's certainly just faster, and it understands the user pretty quick. So, but on the other hand, I don't want to feed it anymore. So, yep, that's what I'm at. So I think I lose some. Okay, so you won't be seeing what I'm doing in my thing, but yeah, it's fine. So wish there would be an adapter, but never mind. Okay, so what is degree of freedom? degree of freedom. Okay, so let's see two.
This is Stephanie from Statistics How To.
How good are your classmates at programming? Some are pretty good, some are pretty terrible, some are decent, some are barely making passing the course. Yeah, mix of both. Yeah, mix of both. Yeah, but at least my classmates are trying to learn, yeah. Well, that's, if they're trying, then that's a good thing, you know, even though they're not like good. Yeah, I used to be terrible at programming as well, and now I'm also terrible too, but not saying I'm better, but I'm better than before because I keep trying. So that's what I tell my classmates if like they feel discouraged or something, because sometimes like when they ask me programming question, I tend to already know the answer, I already know how to do it, because I have did programming before I joined, like years, like 2 or 3 years, and I have made bunch of programs, I did bunch of things, so I know. So, and they are just like, oh, how do you know? And I was like, I did a lot before, so don't feel discouraged, just keep on doing. Well, turn off the train button, then you one step.
.com. In this video, I'm going to explain what degrees of freedom are. Quite a few calculations in statistics have degrees of freedom, and you'll also see them in some tables like this t-distribution table here. Degrees of freedom of an estimate is the number of independent pieces of information that go into calculating that estimate. In order to get those degrees of freedom, you take your sample size and you subtract 1. Let's say you were finding the average weight loss for a low-carb diet. You could use 4 people, giving 3 degrees of freedom, or you could use 99 people, giving 98 degrees of freedom. The formula is degrees of freedom equals n minus 1. N is the number of items in the sample. Why do we subtract 1 from the number of items? Another way to look at degrees. This is Stephanie from statisticshowto.com. In this video, I'm going to explain what degrees of freedom are. Quite a few calculations in statistics have degrees of freedom, and you'll also see them in some tables like this t-distribution table here. Degrees of freedom of an estimate is the number of independent pieces of information that go into calculating that estimate. In order to get those degrees of freedom, you take your sample size and you subtract 1. Let's say you were finding the average weight loss for a low-carb diet. You could use 4 people, giving 3 degrees of freedom, or you could use 99 people, giving 98 degrees of freedom. The formula is degrees of freedom equals n minus 1. N is the number of items in the sample. Why do we subtract 1 from the number of items? Another way to look at degrees of freedom is that they are the number of values that are free to vary in a dataset. What does free to vary mean? Here's an example using the mean or average. Let's pick a set of 3 numbers that have an average of 10. Some sets of numbers you might pick: 9, 10 and 11, or 8, 10 and 12, or 5, 10 and 15. Once you have chosen the first two numbers in the set, the third is fixed. In other words, you can't choose the third item in the set. Let's say I choose 9 and 10 for my first two numbers. The formula for the mean would be 9. Once you have chosen the first two numbers in the set, the third is fixed. In other words, you can't choose the third item in the set. Let's say I choose 9 and 10 for my first two numbers. The formula for the mean would be 9 plus 10 plus some other number divided by 3 equals the 10 for the mean that I'm looking for. I could have picked any number for my first digit. I could also have picked any number for my second digit. Those were free to vary. But when it comes to choosing the third number, there's only one left. I have no freedom to pick that number. So for a set of 3 numbers, the third item gets removed from degrees of freedom. You can find more information about degrees of freedom on statisticshowto.com. Thanks for checking in.
What? Don't understand.
Let me take you back to your first lecture in statistics. Remember that one where you're dealing with means, modes, and medians, and standard deviations? Now everything's going along real smoothly until this equation goes up on the board. And it's about this time that someone sitting in the front row usually will ask the question, like, what's the deal with that n-1 situation? Now at this point the lecturer has exactly 2 options. One, they could kind of hand wave it away and say, look, it's to do with this thing called degrees of freedom. Don't worry about it too much now, hey. Or 2, they could suck it up and actually explain the thing. Now I don't blame lecturers for going with option 1 more often than not. It's a sticky topic, but more's the pity because hiding behind degrees of freedom is actually the foundations of statistics itself. To understand this topic is really to understand statistics. So, with that in mind,
It has been a long time to me to watch YouTube be done.
going to get deep into the weeds.
That's good. Good suggestion, I guess.
My name is Justin Zeltzer from zstatistics.com. Let's do this.
Okay, so here we are with my presentation on degrees of freedom. As you can see before us, we have 4 little sections we're going to get through. We're going to start with the intuition behind degrees of freedom. That'll give us a sort of foundation from which we can look at the practical applications of degrees of freedom. And we'll find out at this point that it's all to do with this concept of estimation. We then break it down and have a look at 3 common scenarios where degrees of freedom are used. The first one is in descriptive statistics, so looking at things like standard deviations, and even skewness and kurtosis and the like. After that, we'll have a look at degrees of freedom in regression. It often pops up when we're looking at regression, and I think I've got a really good visualization for you so you can see how degrees of freedom works there. And finally, we'll have a look at degrees of freedom as they apply in chi-squared tests.
What's this? Oh. I see. Very nice. I think you need to... Yeah, I think I'm good with this. It's fine.
The 2 tests that I'm going to be looking at are the chi-squared goodness of fit test and also the chi-squared test for independence. Now, of course, it's the same concept of degrees of freedom all the way along, but showing you how it applies in these 3 different scenarios will hopefully give you a full picture of what degrees of freedom, and thus statistics, is really about. Now, you might be wondering what this strange item is here on the right-hand side of this presentation. It is indeed a sea urchin, which is going to form the subject matter for all the examples I'm going to be using in this presentation. And specifically, we're going to try to figure out how many spikes do sea urchins have. Now, true story about sea urchins. My brother actually stepped on one when he was about 8 years old, and a full 11 years later, they pulled out one of the spikes from his foot, so it had just been lodged in there for his entire adolescence. Anyway, that's by the by. Okay, so let's move into the intuition. So here I've said consider counting the spikes on a sample of 5 sea urchins. And here is our sample outcome here. We've got 5 individual measurements, each pertaining to the number of spikes on 5 separate sea urchins. Now, as I said in the intro, you've probably met a few of these sample statistics before: the mean, the median, and the standard deviation. Perhaps you haven't quite touched on skewness and kurtosis. We don't really need to worry about what they are at the moment, but I'll throw them in just for good measure. Now, you can get an output like this even from Excel, from Microsoft Excel. You just put in these 5 values into the descriptive statistics dialog, and you press the button, and all of a sudden you'll get these outputs here. Now, the first thing that will happen when you get this output is that your lecturer might ask you, what's your estimate of the mean using these sample statistics? Now, if you think for a moment, you might be a bit perplexed as to why she's used the term estimate. And indeed, our little student here asks, wait, who's estimating? And it's a pretty interesting question. Think about it. We've got 5 observations, and we find the mean of those 5 observations. That's just the average, or the mean, of those 5 observations, right? Why is that an estimate? What possibly could we be estimating? Surely we just have the mean, don't we? Similarly with the median, surely that's just the median. It's not an estimate of the median. Same with standard deviation and skewness. But that's where this topic really comes into contact with the general concept of statistics, because indeed these sample statistics are just estimates of theorized population values. And what that means is, as statisticians, we don't actually care about these 5 sea urchins. We're going to use these 5 sea urchins to try to get some information about what we think the mean is for the population, the whole population of sea urchins. So it's a subtle point, but these sample statistics are actually our estimates for the whole population of infinite numbers of sea urchins. And that's a crucial point to kind of get your head around, which I think never really gets discussed in those first early statistics lectures. So degrees of freedom, which I've shortened to DF here, are just the number of pieces of information we have to estimate the population values. And this definition is actually going to stick with us throughout this entire tutorial. So I'll repeat it. It's the number of pieces of information we have. Sometimes people will say independent pieces of information we have to estimate the population values. So looking at the sample statistics here, let's just pick off the mean and the standard deviation. The sample values are given as x bar, x with a bar on top, and s. But in essence, what they are estimates of the population mean mu and the population standard deviation sigma. And as we're going to find out in the next section, despite the fact we have 5 observations here, it's not so obvious how many degrees of freedom we have in estimating each of our parameters here. It'll turn out we actually only have 4 degrees of freedom with which to estimate sigma. And for skewness and kurtosis, we'd actually only have 3 and 2 degrees of freedom, respectively. But for now, I just wanted to get that point across, that in statistics, we're always taking a sample of something, and we're using that sample to estimate a population value. And so the number of pieces of information we have to estimate that population value is the degrees of freedom.
What? What did he say?
In respect, because we only have 4 degrees of freedom with which to estimate sigma. And for skewness and kurtosis, we'd actually only have 3 and 2 degrees of freedom, respectively. But for now, I just wanted to get that point across, that in statistics, we're always taking a sample of something, and we're using that sample to estimate a population value. And so the number of pieces of information we have to estimate that population value is the degrees of freedom. Okay, so with that intuition now under our belts, let's take a look at how degrees of freedom operates in descriptive statistics more generally. Now, to get our heads around it, I've constructed here the simplest sample I can think of, and that's one where the sample size is exactly 1. So this is 213, the first of our sea urchins. The number of spikes on that sea urchin was 213. So imagine we just had a sample that included that sea urchin. Now, our lecturer might ask here, what is your estimate for the mean mu? Now, our student here might think for a bit, but it's pretty trivial. It's just 213, right? Even though we've got the smallest, crappiest sample possible, your best estimate for where the true population mean is at 213. So in other words, there's one piece of information that we have available, one degree of freedom that we have with which to estimate the population mean. What's your estimate for the standard deviation sigma? Now, even if you haven't dealt too widely with standard deviation, appreciate that it's just a measure of the spread of the particular variable. So looking at our sample here, is it possible to get an estimate of the spread? Our student seems to have a little problem with this, and indeed he should, because we can't generate an estimate for the dispersion here, right? You might think that, okay, we've got a sample of size 1, so it doesn't vary, it doesn't have any kind of variance around it, so the standard deviation should be 0, right?
Yep.
But that's not actually the case. It's not 0, it's actually undefined. And again, that boils down to the idea that we're trying to estimate this population spread. And looking at the sample, we actually have no idea whether it came from a population with a large spread or a very narrow spread. This doesn't give us any information at all. So in fact, we have 0 degrees of freedom and thus cannot estimate it. And even if you had a look at the formula for the standard deviation, even if you don't quite understand it yet, have a look at the denominator. It says n minus 1. So clearly, if we subbed in all the values here and we put in n being 1, we're going to be dividing by 0, which, as you know, mathematically speaking, is an explosion. Okay, so that clears us for the trivial case of having one observation. But let's extend that a little bit further to see what happens when we have a sample of size 2. So here are our first 2 sea urchins, 213 and 180 spikes on each of those respectively. Now let's see what we can do to describe this data set. Here we have it on a number line. There's 180 and there's 213. Now the mean is somewhat trivial. You could sum those two together and divide by 2, and you'd find the mean, which we're giving as x bar here, at 196.5. Now, how would you go about developing an estimate for the spread? Well, we can think about really obvious measures of spread, which include the range, which is just the maximum minus the minimum. But that's pretty basic and ultimately is really affected by outliers. But a more statistically robust measure of the spread might be to say, well, let's try to find the average distance to the mean, or the average deviation to the mean. But of course, you're going to have a problem there, because given that this is the mean, all the positive deviations will exactly equal out with all the negative deviations. So finding the average deviation from the mean is just going to give us a value of 0. So we can't really use that. Using absolute values is also quite clunky statistically. So another option at our disposal might be to find the average squared deviation from the mean, because we know that when we square those deviations, the negative ones are going to become positive again, right? So if we find the average squared deviation from the mean, we're finding some measure of the spread, a very statistically robust measure of the spread of this distribution. And indeed, that's what variance is. The statistical measure of variance is the average squared deviation from the mean mu. Now we'll get to degrees of freedom in a second, but you can see how this will congeal all of our knowledge of other aspects of statistics to get there, right? Let's keep going. So let's have a look at the formula for variance. It's the sum of x minus mu all squared on n. That's the sum of those squared deviations from the mean divided by the number of observations, therefore giving us the average squared deviation from the mean. But you'll notice it actually has the population mean here, as it should, because that's the true mean. But on this number line, where is that population mean? Appreciate that it could be all the way down here, and maybe our sample just happened to be 2 fairly large sea urchins. Or alternatively, the population mean might be all the way up here. But wherever that particular population mean is, theoretically we could find an average squared deviation from that population mean. And we'd have this statistically robust calculation for the spread of the data, right? Cool, well that's all well and good, but guess what? We don't have the population mean. We only have a sample of size 2. We have no idea what the population mean is. The best we can do is use the sample mean as an estimate for the population mean, right? So our formula is going to change a little bit. Instead of using this sum of the squared distances from the population mean, we're going to do the sum of the squared distances from the sample mean x bar. And instead of calling it sigma squared, we're now going to call it s squared, which is the sample variance. But there's a problem with this formula. We know that originally we wanted the average squared deviation from the population mean, but of all the places that that population mean could be, our calculation is minimized if we put it bang on that sample mean, which is exactly what we're doing. If the population mean was anywhere else, this calculation would be larger. So to account for the fact that x bar is effectively a best case scenario for mu, we need to inflate our estimate for the population variance somewhat. And that's why the denominator is no longer n, but is n minus 1, artificially increasing that calculation. Now, of course, this is the variance, and to get to the standard deviation, you're going to be taking the square root of all that. But the same principle applies. The degrees of freedom here is still n minus 1. It's only with that second observation that we were allowed to get a calculation for the variance and thus the standard deviation.
What?
Now, I go into the variance and standard deviation in a little bit more depth in a video that I'll put the link up for here. But let's carry on to see how degrees of freedom applies to regression. Now, if you've not dealt with regression before, just appreciate that it's a way of assessing the relationship between 2 variables. And here the question might be, how does water temperature affect the number of spikes found on sea urchins? And indeed, we have our 2 variables here. The temperature is on our x-axis, and the number of spikes in our sea urchins is on the y-axis. So with whatever sample we get, a regression just tries to put a line of best fit through that sample. But again, there's a certain number of degrees of freedom that we have here as well. And to understand it, let's sort of pare it back to the minimum possible number of observations that we could think of in this scenario. So here's the question. Our lecturer asks, what's the minimum number of observations you require to run this regression, where we've got spikes as a function of the temperature? Now, our student here might say, well, look, I think you only need 2 observations, because with 2 observations, you can draw a line of best fit, and therefore you can get an assessment of the gradient between these 2 variables. And you can also get an assessment of the y-intercept. And to some degrees, that's correct. But in fact, this is where we have to ask ourselves that same question. What are we estimating here? Well, a regression not only estimates these betas, which is the gradient and the y-intercept respectively, but it also estimates the uncertainty we have with those values. Now, remember your regression output? That first column in your regression output deals with the coefficients, and then everything else will assess the standard errors, the t-stats, the p-values. That's all to do with the uncertainty around those coefficients. So realistically, with just 2 observations, we cannot estimate that uncertainty, right? That line of best fit is going to go straight through those two observations, no matter where they are. And it's only with that third observation that we indeed have what we call a degree of freedom, such that the regression line can cut through those points and we can finally get a little bit of error in there that we can use to estimate that uncertainty.
Wait, so degree of freedom is the amount of error, like estimate of error that could happen, or it is to make sure that you add on some errors when you calculating. What? This make no sense. Whoa, what's this? Whoa, Uniday? Damn. 15-inch. Yay. Cool. Very nice, very nice. M1, this is M2. M2. Wow. Okay. Yeah, I might need a break. God damn it. This is difficult.
we're going to do the sum of the squared distances from the sample mean x bar. And instead of calling it sigma squared, we're now going to call it s squared, which is the sample variance. But there's a problem with this formula. We know that originally we wanted the average squared deviation from the population mean, but of all the places that population...
Let me take you back to your
hand side of this presentation. It is indeed a sea urchin, which is going to form the subject matter for all the examples I'm going to be using in this presentation. And specifically, we're going to try to figure out how many spikes do sea urchins have. Now, true story about sea urchins. My brother actually stepped on one when he was about 8 years old, and a full 11 years later, they pulled out one of the spikes from his foot. So it had just been lodged in there for his entire adolescence. Anyway, that's by the by. Okay, so let's move into the intuition. So here I've said, consider counting the spikes on a sample of 5 sea urchins. And here is our sample outcome here. We've got 5 individual measurements, each pertaining to the number of spikes on 5 separate sea urchins. Now, as I said in the intro, you've probably met a few of these sample statistics before: the mean, the median, and the standard deviation. Perhaps you haven't quite touched on skewness and kurtosis. We don't really need to worry about what they are at the moment, but I'll throw them in just for good measure. Now, you can get an output like this even from Excel, from Microsoft Excel. You just put in these 5 values into the descriptive statistics dialog, and you press the button, and all of a sudden you'll get these outputs here. Now, the first thing that'll happen when you get this output is that your lecturer might ask you, what's your estimate of the mean using these sample statistics? Now, if you think for a moment, you might be a bit perplexed as to why she's used the term estimate. And indeed, our little student here asks, wait, who's estimating? And it's a pretty interesting question. Think about it. We've got 5 observations, and we find the mean of those 5 observations. That's just the average, or the mean of those 5 observations, right? Why is that an estimate? What possibly could we be estimating? Surely we just have the mean, don't we? Similarly with the median, surely that's just the median. It's not an estimate of the median. Same with standard deviation and skewness. But that's where this topic really comes into contact with the general concepts of statistics, because indeed these sample statistics are just estimates of theorized population values. And what that means is, as statisticians, we don't actually care about these 5 sea urchins. We're going to use these 5 sea urchins to try to get some information about what we think the mean is for the population, the whole population of sea urchins. So it's a subtle point, but these sample statistics are actually our estimates for the whole population of infinite numbers of sea urchins. And that's a crucial point to kind of get your head around, which I think never really gets discussed. Sea urchins, to try to get some information about what we think the mean is for the population, the whole population of sea urchins. So it's a subtle point, but these sample statistics are actually our estimates for the whole population of infinite numbers of sea urchins. And that's a crucial point to kind of get your head around, which I think never really gets discussed in those first early statistics lectures. So degrees of freedom, which I've shortened to DF here, are just the number of pieces of information we have to estimate the population values. And this definition is actually going to stick with us throughout this entire tutorial. So I'll repeat it. It's the number of pieces of information we have, sometimes people will say independent pieces of information we have, to estimate the population values. So looking at the sample statistics here, let's just pick off the mean and the standard deviation. The sample values are given as x bar, x with a bar on top, and s, but in essence what they are estimates of the population mean mu and the population standard deviation sigma. And as we're going to find out in the next section, despite the fact we have 5 observations here, it's not so obvious how many degrees of freedom we have in estimating each of our parameters here. It'll turn out we actually only have 4 degrees of freedom with which to estimate sigma. And for skewness and kurtosis, we'd actually only have 3 and 2 degrees of freedom respectively. But for now, I just wanted to get that point across that in statistics, we're always taking a sample of something, and we're using that sample to estimate a population value. And so the number of pieces of information we have to estimate that population value is the degrees of freedom. Okay, so with that intuition now under our belts, let's take a look at how degrees of freedom operates in descriptive statistics more generally. Now, to get our heads around it, I've constructed here the simplest sample I can think of, and that's one where the sample size is exactly 1. So this is 213, the first of our sea urchins, degrees of freedom. And as we're going to find out in the next section, despite the fact we have 5 observations here, it's not so obvious how many degrees of freedom we have in estimating each of our parameters here. It'll turn out we actually only have 4 degrees of freedom with which to estimate sigma. And for skewness and kurtosis, we'd actually only have 3 and 2 degrees of freedom respectively. But for now, I just wanted to get that point across that in statistics, we're always taking a sample of something, and we're using that sample to estimate a population value. And so the number of pieces of information we have to estimate that population value is the degrees of freedom. Okay, so with that intuition now under our belts, let's take a look at how degrees of freedom operates in descriptive statistics more generally. Now, to get our heads around it, I've constructed here the simplest sample I can think of, and that's one where the sample size is exactly 1. So this is 213, the first of our sea urchins. The number of spikes on that sea urchin was 213. So imagine we just had a sample that included that sea urchin. Now, our lecturer might ask here, what is your estimate for the mean mu? Now, our student here might think for a bit, but it's pretty trivial. It's just 213, right? Even though we've got the smallest, crappiest sample possible, your best estimate for where the true population mean is at 213. So in other words, there's one piece of information that we have available, one degree of freedom that we have with which to estimate the population mean. What's your estimate for the standard deviation sigma? Now, even if you haven't dealt too widely with standard deviation, appreciate that it's just a measure of the spread of the particular variable. So looking at our sample here, is it possible to get an estimate of the spread? Our student seems to have a little problem with this, and indeed he should, because we can't generate an estimate for the dispersion here, right? You might think that, okay, we've got a sample of size 1, so it doesn't vary, it doesn't have any kind of variance around it, so the standard deviation should be 0, right? But that's not actually the case. It's not 0, it's actually undefined. And again, that boils down to the idea that we're trying to estimate this population spread. And looking at the sample, we actually have no idea whether it came from a population with a large spread or a very narrow spread. This doesn't give us any information at all. So in fact, we have 0 degrees of freedom and thus cannot estimate it. And even if you had a look at the formula for the standard deviation, even if you don't quite understand it yet, have a look at the denominator. It says n minus 1. So clearly, if we subbed in all the values here and we put in n being 1, we're going to be dividing by 0, which, as you know, mathematically speaking, is an explosion. Okay, so that clears us for the trivial case of having one observation. But let's extend that a little bit further to see what happens when we have a sample of size 2. So here are our first 2 sea urchins, 213 and 180 spikes on each of those respectively. Now let's see what we can do to describe this data set. Here we have it on a number line. There's 180 and there's 213. Now the mean is somewhat trivial. You could sum those two together and divide by 2, and you'd find the mean, which we're giving as x bar here, at 196.5. Now how would you go about developing an estimate for the spread? Well, we can think about really obvious measures of spread, which include the range, which is just the maximum minus the minimum. But that's pretty basic and ultimately is really affected by outliers. But a more statistically robust measure of the spread might be to say, well, let's try to find the average distance to the mean, or the average deviation to the mean. But of course, you're going to have a problem there, because given that this is the mean, all the positive deviations will exactly equal out with all the negative deviations. So finding the average deviation from the mean is just going to give us a value of 0. So we can't really use that. Using absolute values is also quite clunky statistically. So another option at our disposal might be to find the average squared deviation from the mean, because we know that when we square those deviations, the negative ones are going to become positive again, right? So if we find the average squared deviation from the mean, we're finding some measure of the spread, a very statistically robust measure of the spread of this distribution. And indeed, that's what variance is. The statistical measure of variance is the average squared deviation from the mean mu. Now we'll get to degrees of freedom in a second, but you can see how this will congeal all of our knowledge of other aspects of statistics to get there, right? Let's keep going. So let's have a look at the formula for variance. It's the sum of x minus mu all squared on n. That's the sum of those squared deviations from the mean divided by the number of observations, therefore giving us the average squared deviation from the mean. But you'll notice it actually has the population mean here, as it should, because that's the true mean. But on this number line, where is that population mean? Appreciate that it could be all the way down here, and maybe our sample just happened to be 2 fairly large sea urchins. Or alternatively, the population mean might be all the way up here. But wherever that particular population mean is, theoretically we could find an average squared deviation from that population mean. And we'd have this statistically robust calculation for the spread of the data, right? Cool, well that's all well and good, but guess what? We don't have the population mean. We only have a sample of size 2. We have no idea where the population mean is. The best we can do is use the sample mean as an estimate for the population mean, right? So our formula is going to change a little bit. Instead of using this sum of the squared distances from the population mean, we're going to do the sum of the squared distances from the sample mean x bar. And instead of calling it sigma squared, we're now going to call it s squared, which is the sample variance. But there's a problem with this formula. We know that originally we wanted the average squared deviation from the population mean, but of all the places that that population mean could be, our calculation is minimized if we put it bang on that sample mean, which is exactly what we're doing. If the population mean was anywhere else, this calculation would be larger. So to account for the fact that x bar is effectively a best case scenario for mu, we need to inflate our estimate for the population variance somewhat. And that's why the denominator is no longer n, but is n minus 1, artificially increasing that calculation. Now, of course, this is the variance, and to get to the standard deviation, you're going to be taking the square root of all that. But the same principle applies. The degrees of freedom here is still n minus 1. It's only with that second observation that we were allowed to get a calculation for the variance and thus the standard deviation. Now, I go into the variance and standard deviation in a
elements of data points that you have. So if I have 55 students here, I compute all your scores, I sum them all up, I divide by 55, I get the average score, right? I get the average score of that person. What on a space, if you have to plot all these out, that point that is the average is actually, I already covered this in the first class, remember? Is at the center. Right, is at the center. So typically, when we only have one dimensional data point, we say, right? We say there could be a student over here, there could be a student over here, or maybe here and here and here and here and here, right? So let's say if this is one on a scale of 100, this is 0, right? Maybe someone get 20, 22. 38, 45, and maybe this is a 72, 81, and 90, something like that. Okay? On a scale of 1, 2, 3, 4, 5, 6, 7, let's give one more. 48 over here. Okay? So out of 8 students, we got the scores. Okay? If you add all these up and divide it by 8, what do you get? That's 42. 42, and that's 80, 336, 416, correct? right? And 52 will be somewhere around here. Right? So you have average would be, in the middle between all these different points, right? And that's the reason why when you see a student having a GPA of 3.99, you're pretty sure that it's mostly 4. Because otherwise, if they had a 2s and 1s and 2.25 in there, it's not going to be 3.99, right? It has to be a lot of 4s. Okay, so this is how you would be computing the average. Pretty simple. The summation of all elements, okay? Sum them all up, divided by the total number, n, okay? But let me try to answer this. Let's do two-dimensional this time, for the sake of trying to understand, right? Let's do two-dimensional. So here we go, 1, 2, and let's say over here is I always want to do weight and heights. Is it okay if I do weight and height in here? Weight and height, right? Let's do weight and heights, and basically then you have different numbers. Let's say let's just do with 5 people, right? So this is, let's say over here is like 100 over here. That's the weight, and the height would be around 200. I hope there's no one taller than 200 centimeters, right? Okay, so I'll start with mine. So mine is 94, somewhere around here, and 176. So over here it's 94, 176. Right? 8.750. There's no vectors, it's going to be the same. So you can find averages for just about every data set, okay, with different number of attributes, okay, in much the same way that you do for one-dimensional data points. Okay? Okay? You find the mean for this purpose. Now, what I also want to do, apart from doing this, is I also want to find like the variations. What is the variability? Okay? Let's start off once again with only one dimensional data point, 60, 35, 45, 55, 65, and 94. 35, 45, 55, 65, and 94. Am I correct? Okay, so 5 data points. Okay, how do I find the variations? How do I find the variability in all these? Let's start simple first before we go on to the actual formula. I want you to think about it for a moment. Okay, let's start off. If 5 numbers is too difficult for you, or if 5 numbers is too difficult for you, how about I start with 2? I say I want to find the variation between 35 and 45. What's the variations here? Obvious. What's the difference between 35 and 45? 10, right? So we say these two numbers differ by 10. What about 35, 45, and 55? Now I have 3 numbers. If I have 3 numbers, intuitively I would say what? I need to find the variation to this guy, right? variation between this guy and this guy, and the variation between this guy and this guy. So this one is 10, this one is 20, this one is also 10. But I have 3 values, what do I do with it? Average of what? Of the variations instead, right? So you can take 10 plus 10 plus 20 divided by 3. That's actually 40 divided by 3. Correct? That's finding variations. But when you actually do the formula, one problem that you're going to have is that how do you know which one minus which one? Are you going to take 35 minus 45 or 45 minus 35? If you take 35 minus 45, you're going to get minus 10. Right? If you take 45 minus 35, it's going to be just 10. So, how do we do it? One way, of course, would be to take the absolute, right? Just put in the absolute value and just divide. Right? There's actually a formula like that as well. Okay? That's actually a formula. Another way would be to square it. Right? So it means that you take this, square, and this, square, right? Gives you, and then you sum them up, and then you divide by the total number of differences, not the total number of data points, right? You have to divide by the total number of differences, and then what do? Then you get the value. We call that value the variance.
Hello.
Right? Call that value the variance.
Oh, what?
Now, population variance.
Variance.
Welcome to the
Is it necessary?
It's a parameter where you actually use divided by n. Sample variance is the one where you use, as you say, you divide it by the degree of freedom rather than n. And degree of freedom is just easily n minus 1. Okay? Just very easily n minus 1. The proof for degree of freedom is a bit more complex to be done within this, right? But I can give you an analogy of why we use degree of freedom instead of n. Okay, degree of freedom is actually a property that will allow, because when you actually have, like, for example, 3 values, and basically if you divide it by 3, okay, we call it the it's a bit too difficult to explain it without understanding the triangular Anyway, for now, just
โอเคนะครับในหนึ่งในเรื่องที่สำคัญที่สุดเวลาที่คุณจะออกแบบกลไกหรือวิเคราะห์กลไกนะครับก็คือคุณจะต้องวิเคราะห์ที่เราเรียกว่า degree of freedom หรือ DOF ก่อนนะครับ degree of freedom นะครับ degree of freedom เนี่ยในไทยเนี่ยนะครับมันมีการแปลเป็นศัพท์ไทยเนี่ยหลายศัพท์มากนะครับบางคนแปลว่าระดับขั้นเสรีนะครับระดับขั้นเสรีเนี่ยเขาคงแปลว่า freedom เนี่ยแปลว่าเสรีนะครับและ degree ก็คือว่ามันมีระดับหรือมีขั้นของเสรีขนาดไหนนะครับแล้วก็มีคนหนึ่งแปลเขาแปลว่าเป็นองศาอิสระนะครับก็คงแปลดีกรีว่าเป็นว่าองศาอิสระนะครับแล้วก็ใน textbook มีการพูดถึง mobility นะครับมันเป็นศัพท์เดียวกันทั้งหมดเลยนะมันกำลังพูดถึงพารามิเตอร์ตัวหนึ่ง performance index ตัวหนึ่งที่บอกว่ากลไกเนี่ยมีศักยภาพในการเคลื่อนที่หรือมีความอิสระในการเคลื่อนที่กี่ทิศทางนะครับทีนี้ degree of freedom เนี่ยมันมีอิสระในการเคลื่อนที่กี่ทิศทางเนี่ยมันเป็นนามธรรมนับได้ยากนะครับเพราะฉะนั้นเราก็จะมีการพูดถึงนิยามของ degree of freedom เนี่ยใน2นิยามหลักนะครับนิยามแรกก็คือจะบอกว่า degree of freedom หมายถึงนะครับความมีอิสระในการเคลื่อนที่เขาก็จะปิดกล่องนะ
Degree involves degrees of freedom. It is a coin toss whether we got tails.
Okay, so here are some practice situations for the Lagrangian. I have a simple pendulum. Here I have a cart that can move back and forth with the pendulum. Here I have a pendulum on a cart with a spring. Here I have a pendulum cart and the string is a spring. And then finally this is a driven cart with a swing. So the question is, how many degrees of freedom are there for each one? And which one is the hardest to solve? So this is a 1 degree of freedom because you only need one angle. This is 2 degrees of freedom because you need the position of the cart and that one. This is 2 degrees of freedom. This is 3 degrees of freedom because you're the cart, the angle, and the stretch. And this is just 1 degree of freedom. So that one, this is the easiest. This one's actually not so difficult to solve.
Number of
What is degrees of freedom? It is used in statistics, it's used in economics, it's a very important concept. So it's like that. For example, I give you 5 equations and there are 7 unknowns, or let it be 3 unknowns. So in order to find it, you can utilize any 3 equations and you can keep 2 aside. So that's it. So the 2 extra equations which you don't use, that gives you the freedom. So total number of equations minus total number of unknowns gives you the degrees of freedom. So in any kind of statistical analysis or econometric propagation, so this you need to remember that how much you take in and how much you leave. Now a system is only solvable if df is greater than equal to 0. df equal to 0 so allows you to solve, but if df is negative, so you don't have that freedom to solve it, because how can you solve x plus y equal to 16 and finding the exact values of x and y? So the exactness is not being defined, so degrees of freedom is needed in order to find the solution.
In this video, I will discuss the concept of degrees of freedom. So in summary, degrees of freedom is a fundamental concept in data science that helps to understand the amount of independent information available for estimating parameters or making statistical inference. So you will often hear a statistician and data scientist say that do not add more variables because you will not have enough degrees of freedom. Let's understand this statement using multiple linear regression as an example. So in multiple linear regression, adding more independent variables reduces the degrees of freedom. The more variables you have, the higher the amount of variance you can explain. Even if each variables doesn't explain much, adding a large number of variables can result in very high values for your R squared value. And in this video, I will discuss the concept. In this video, I will
किसी भी मैकेनिक
You need to know that degree of freedom is simply just n minus 1. If you're interested in learning about degree of freedom, you can start by looking it up. And if you want to, we can talk about it, okay? So, exactly that, right? Okay, we call it variance. And variance, we normally use S squared to denote that we never actually take away the square part, right? We never actually take away the square part. But if you want to take away the square part, sure, why not? It's just standard deviation.